Well, hello everyone. Good evening. It looks like we are live, and as usual, I'm going to wait just a couple of seconds just to make sure everything is working good. Um, everyone hear me all right? I'm here today with Leophilius and Jordan, and we're going to be discussing physics and how physics refutes young Earth creationism, specifically when we get to some of the equations in physics and how it relates to the technology that we all depend on. So, Leo, Jordan, welcome back to my channel. Feel free to introduce yourself. Leo, let's start with you.
Yeah, I'm a guy that does stuff on YouTube who has no degrees but has spent the last 10 years with a almost obsessive interest in physics. I've read a few textbooks, done lectures through MIT OpenCourseWare, Yale courses, Stanford. I'm learned in the subject, but I'm by no means a professional, and I wouldn't claim to be.
Yep. And Jordan, please feel free to introduce yourself. Welcome back.
My name is Jordan. I am a mechanical and nuclear engineer. So I'm not a scientist or a physicist, but my coursework did include some physics, and I like to think I'm reasonably well informed when it comes to nuclear processes. I want to apologize ahead of time if I'm kind of mumbling. Like I told the guys, I've just recently got a gum surgery, so I can only open my mouth so much. So hopefully you guys can still understand what I'm saying.
Okay, sure. So, where do we want to begin? Um, I think we should start with, since you only have a couple of minutes, let's start with some of the nuclear physics side of it and how it relates to, say, relativity and stuff like that. And we can
I
talk
think
about,
that's a.
and we can talk about relativity, Maxwell's equations, and all that type of fun stuff.
Could I suggest going with the nuclear? I think, and this is something that I know Jordan has spoken about. He's hammered home on many other channels, but I think it's a really, really good point to start with is nuclear decay and how that relates to dating rocks and thereby the age of the Earth. I always think that's a really good place to start when it comes to YEC.
Oh, yeah, absolutely. So, Jordan, you're the expert with that. So, I'll let you have the floor.
So when it comes to radiometric dating, which is the what we call the dating method where we're dating rocks, there's a couple things on that. First of all, there's a variety of different dating methods, and each of them work on different isotopes, and they have their own different assumptions. So an objection that works for one type of dating method won't necessarily work for all of them. Also, because of the different half-lives of the isotopes involved, not every dating method can be used for every date range. So like if we're dating the age of the Earth, which is billions of years old, radiocarbon dating isn't going to be useful for that because carbon-14 has a half-life of like 5,500 years. So you can't use that to date the age of the Earth, if that makes sense.
Right.
But for long-lived isotopes like uranium, for instance, you can get dates in the billions of years, which puts a lower limit on the age of the Earth. Obviously, the Earth can't be any younger than any of its constituent rocks. So if you get an age of 3 billion years, then that means the Earth is necessarily older than 3 billion years.
Right. And one of my personal favorite things in geology is the natural nuclear reactor, which pretty much definitively proves that the Earth has to be a minimum of 2 billion years. So feel free to talk a little bit about that.
So yeah, you can. So creationists like to sharpshoot radiometric dating by saying that you have to know the initial isotopic prevalence and stuff like that, and those aren't necessarily true. But another way outside of radiometric dating that we can use nuclear physics to date the Earth is through other phenomena such as the Oklo phenomena. So in Oklo, there's a uranium mine, and when they were excavating uranium, they measure its enrichment because of proliferation concerns. And they also want to know how much uranium they're getting. So natural uranium right now is 0.7% enriched. That means about 0.7% of it is U-235. The rest is U-238. U-235 is the fissile stuff, the stuff you make bombs and nuclear reactors out of. And they pulled some rock out and it was depleted. I can go more into detail if you want, but basically, long story short, is The way that they found depleted uranium, and then they also found isotopes that only come from fission from nuclear reactors. So what that indicates is that at some point, a chain reaction of fission happened.
Right.
Obviously, there was no nuclear reactor built there, so that means it was a natural one.
Right.
In order to have a chain reaction in the presence of water, you need uranium enriched to 3%. So the way that works is U-235 decays faster than U-238. So as we go forward in time, uranium is becoming less and less enriched. Well, if you go backwards, uranium becomes more enriched. If you can do the math to determine how long that would take. And it turns out it's 1.8 billion years to get to 3% enrichment. So 2 billion years, because you're going to need to be a little bit more than 3%.
Right.
So that tells us that 2 billion years of decay at today's rates necessarily happened. So if half-lives have not changed, then the Earth is necessarily older than 2 billion years.
Right. And obviously, in the 70s, when it was discovered, you were in the height of the Cold War. So obviously, everyone was like unnerved when they found that the uranium isn't as enriched as it should be.
Right.
And
The initial
right.
worry was that someone had stolen some uranium.
Right. Exactly. And of course, if it goes faster, then everyone's dead. And we spoke
Yeah.
about the heat problem numerous times.
So one way that the creationists like to pretend that radiometric dating or the Oklo phenomena or whatever is answer. One way they address that is they say, okay, well, the Oklo happened, but all we need is 2 billion years worth of decay, but it didn't necessarily have to take 2 billion years. What if we sped it up so that we decayed it really fast? So we've only got 6,000 years. Typically, they like to put it in the flood year. So they'll say, what if you weren't there, you didn't know, blah, blah, blah. You know, what if somehow God tinkered with physics and made half-lives much shorter than they are currently, such that we could get Oklo during the flood. So basically, God super sped up half-lives, so you get all that necessary decay in 1 year. And there you go. You can have the appearance of age or whatever without actual age.
I have a question about that, if I may, Jordan. Let's just grant, for the sake of this question, that God can do miracles and all this fancy magic stuff is real. If something like that actually did happen, there would be records of that in geology, wouldn't there? Of it, like
Yes.
a period of accelerated nuclear decay.
So, well, I mean, I guess it depends on how much interference you're allowing God to have. Like, if you have an omnipotent person, an omnipotent being who can alter the laws of physics, then it's conceivable he could. I mean, it's conceivable he could do anything, right? So he could like
erase that evidence.
Yeah, he could erase the evidence and do but leaving that aside, because I don't think many people, even creationists, would say that. Let's say all he did was accelerate or change the decay constant such that it went faster. That would have implications that would leave records. Well, and as a matter of fact, the implication would be that the Earth's crust would vaporize. So the whole idea of records is kind of a moot point. But at the very least, you'd have things like right now there's uranium halos and fission tracks in rocks. So we can see the indication of damage from radiation in the rock. It's discoloration from the high energy particles that are released during nuclear decay. That damage doesn't last forever. If you heat up the rock, it goes away, you know? And so if you had this amount of decay, it would release a lot of heat. So you'd think that it would wipe away those records. So they need accelerated decay in order for those records to happen, because fission halos are another thing that not fission halos, uranium halos are another thing that require a lot of time to make. It takes millions of years worth of radiation for that to happen. But the process by which it would happen fast would also produce enough heat to wipe it away.
Yep.
No, that
And
makes sense.
right. And oh god.
Now, if you're asking if like maybe I don't know of other than a byproduct of like the heat and things like that, that's what would leave the record. I don't know if somehow you just ignored the heat or was magically transported away or something. I don't know if you could distinguish between like 1,000 decays that happened in a second and 1,000 decays that took a year. I'm not sure.
Okay.
But you can't just take away the heat, so it's kind of a kind of a moot point. On the heat thing, so when just a quick primer on radioactivity for anyone who isn't aware. When I talk about speeding it up, why does it matter, right? It's like, who cares if it's faster or slower as long as it just happened? Well, when an unstable atom, and I'm probably going to use the term isotope interchangeably. An isotope is just a name for an atom. You can have the same atom with a different number of neutrons, and all of those are isotopes of the element. So if I say isotope, that's all it means. Anyway, so when you have an unstable atom, it decays over time by releasing something, maybe alpha particle or a beta particle or some gamma rays or something. Those particles have energy, and when they hit other things, it'll turn to heat. So if you have a atom in some rock and it decays, it's going to release heat eventually. That's how it's going to be expressed. So
right.
Every decay is going to lead to heat. Now,
right.
If you condense 2 billion years worth of decay into a billion years, or into a year, that's what they want to do in order to make their radiometric dating work or make Oklo work or whatever, then you are also condensing 2 billion years worth of heat into 1 year. And that is not easy to take care of. I mean, even just the decay itself has problems, but that also leads to follow-on problems, specifically the heat problem.
Right. And I think it's important to point this out that asteroids and moon rocks actually do give a very important independent check to the rocks we have on Earth, because they are less likely to be contaminated. And we've actually directly radiometric dated rocks on Mars in situ. So these act as an independent check to, and if this happened during the flood, then the asteroids, moon rocks, and Mars rocks should not have been affected. To make matters worse, Dr. Andrew Snelling looked at these meteorites and concluded that there's no evidence of accelerated nuclear decay within these asteroids. So that pretty much takes care of all of that right there. So that's pretty much the checkmate for accelerated nuclear decay. Smoking Saint asks, since you're on this topic, can you touch on the hydroplates theory? Which I'm sure we could touch up on a little bit.
Basically, the hydroplate theory, as I understand it, is you've got these plates that were vibrating because of the forces of the flood, the fountains of the deep, whatever. And the vibrating of these plates led to a piezoelectric effect, like lightning bolts underground, basically. And those high energy streams of electricity led to fusion, which created all of the radioactive elements that exist. So they get around accelerated decay by saying there were no radioactive elements prior to the flood, and this is how those radioactive elements came into being. That's my understanding of it.
Right. The big problem with that, of course, is that we know that radioactive elements exist in stars and outside the...
Yeah, you basically have to say that, okay, let's say that I am not certain that that's a reasonable... I'm pretty sure it's not a reasonable model, but even aside from the model problems, you'd have to say then, okay, God made radioactive elements everywhere else in the universe, but not on Earth, because no amount of vibrating plates on Earth is going to cause uranium to show up in a star, thousands of light years away. But we can detect the presence of uranium in those stars through their spectral lines. So We
Yeah.
know that radioactive elements exist outside of the Earth. Where did those come from? Couldn't have been Earth's hydroplates.
Yeah.
Not to mention the fact that radioactive elements don't just come in the forms of heavy elements. Like, it's not just uranium and thorium.
Isn't tritium the third isotope of hydrogen? Isn't that radioactive?
It is. Tritium is a radioactive isotope of hydrogen, so some amount of the water you drink is radioactive. And it's a small amount. It's not enough to hurt you. It is enough to hurt you if decay is accelerated. But that carbon-14 in the atmosphere, that is caused through high energy particles coming from the sun, exciting nitrogen. And so, but like, where did that, like how does hydroplate affect that? I don't see how it could possibly affect that. I mean, that at that point, God then also would have to say, would shield the atmosphere from all these high energy particles. I don't know. It doesn't seem like a cohesive model.
Right, and you also have to have an even bigger problem. Let's just ignore the radioactive decay and the heat problem associated with that. You're going to be creating massive tsunamis, massive earthquakes, and the heat just from the friction alone, and that alone is going to be catastrophic in and of itself. And even worse is, what is the mechanism for how the mountain of the Great Deep even broke up? How did the water get into this position to begin with? Where did it all come? Where did it all go? And what is the basic mechanism for this? Yeah. So without that, it's not a viable model.
So I'm just trying to think if there's any other stuff that comes to the radiometric dating and stuff that are common YEC problems. So one thing that is a very common YEC objection to radiometric dating is they say it's based on unevidenced assumptions. Things like you have to know the initial composition of the rock, and you can't possibly know that because you weren't there, right? So for those who don't who aren't familiar with radiometric dating, like I said, every method's a little different, but basically you look at the amount of isotope today. So the parent isotope decays and makes a daughter isotope, 1 for 1, unless there's fission involved, which there isn't typically. So if you knew hypothetically how much parent there was to begin with, and then you can see how much parent there is now, or how much daughter there is now, you can just apply the half-life, do some math, and it'll give you an age. That's the idea. Right. Now, of course, we don't know how much parent was there originally. So how do we get by that? Well, we can use a method called isochron dating. So in addition to radioactive isotopes of an element, there are often non-radioactive or non-radiogenic isotopes of that element. So as an example, in rubidium strontium dating, there are radiogenic isotopes of strontium. Rubidium decays into strontium. Okay, it decays into strontium 87, I think. It's either 87 or 86, and the other one's not radiogenic. But so there's a kind of strontium that comes from the rubidium decay. There's another kind of strontium that does not come from decay. It's stable. It doesn't go away. It just sits there forever. Okay. And so that amount of strontium was there to begin with. And so mathematically, what we can actually do is we can measure the ratio of parent isotope today to stable isotope today, and the ratio of daughter isotope today to the stable isotope today, and then do some math, and that gives us an age for the sample without ever having to know the initial composition. And if you don't believe me, which why should you believe me? I haven't showed you anything real. I actually have a proof that I can put on the screen right now if you want. I can drop a link in the chat if anyone's interested. So let me share my screen if you don't mind.
While you're bringing that up, I did want to make a quick comment when David brought up dating asteroids. We've also, and Mars, and we have dated a few asteroids, and we've also dated Mars. All of the ages comport with the age of the Earth. Now, that doesn't mean that they're exactly the same, but they're in a range where we can reasonably conclude they all formed at roughly the same time and in roughly the same way, which concords with the, the accretion disk, planetary disk model for the formation of the Earth and all the other planets. We've also dated the Moon, and the ages for the Moon are a little bit interesting. They range from 3 to 4.5 billion years, which does comport with what's often called the Theia collision hypothesis, where a Mars-sized object would have struck the Earth when the Earth was something like 200 to 500 million years old, which is why we would get roughly about 1.5 billion years in difference in age, because you would have the original material from the Earth, which would be older, and then the younger material from the object that struck the Earth 500 million years after the Earth formed.
Right.
Yeah, and if things weren't made all at the same time billions of years ago, there's no reason why those ages would match.
Exactly.
Right. And an important point to note is that every radiometric dating method has their own margin of error. So when we have 5 different dating methods, and all of these dating methods are well within each other's margin of error, that adds very important checks to our calculation.
Yeah.
The data has been corroborated, or the data corroborates each other.
And they
Right.
wouldn't, those methods wouldn't need to agree. Like if God just made the Earth 6,000 years ago, there's no reason to make all of these isotopic ratios such that they would all match. Like each dating method uses a different set of isotopes, many of whom decay in different ways. There's no reason why they would just randomly match, unless God specifically made it like in a deceitful way, like so that it's impossible to tell. Yeah.
Right. And to me, that would go against God's character.
I would think. So can you guys see? I don't know how well you can actually see
it can be seen, but it is a little bit difficult.
All right. So
and that's a bit better, but if it can be made larger,
Yeah.
I think that would be.
let me see. I can pull the actual. Is that a way you should read?
Yeah, that's better.
Okay. So I'm gonna post a link to this doc in the thing, so anyone who wants to like dig into the math can if they wish. But this is a proof I wrote for the isochron formula that you'll see. This is the equation that you'll see in like textbooks and stuff. Again, I'm not going to dig all the way in, but basically you're taking this is the formula for radioactive decay, how many atoms there are now versus how many there were before with some, with the decay constants. And if you take that down through these various relations, you get to this equation here. This amount here. So what this equation is, it's in the form of y equals mx plus b. This is y. This is m.
So
this is
slope
x,
intercept.
and this is b. Yeah, It's just the equation of a straight line. So what we can do with that is if we can graph the x and y coordinates, and you get a bunch of them, you can calculate m and b, or you can estimate it using just the x and y coordinates. So if we know y and we know x, and we have many different points, we can use the least squares regression to get m and b. Okay. Again, I'm going to post this, so if you want to check my proof, please do. But anyway,
And
so this, go ahead.
Yeah, no, finish.
So this is y. dref here, that's the stable isotope today. This is the amount of daughter isotope. The amount of daughter isotope today equals the initial amount plus however much parent decayed. So we don't know what the initial amount is. We don't know how much the parent decayed, but whatever it was, the summation of those two things is how much daughter there is today, right? So this term, daughter today, stable today. So that's something we can currently measure. Then x here, again, this is stable. dref is just stable. And then how much parent is there? Well, there's however much there was originally minus however much decayed. We don't know how much was there originally. We don't know how much decayed, but whatever it was, the summation of those two things will equal the amount of parent today. So you've got parent today over stable today. That is, again, something we can measure right now. This here is the change in parent over time. that'll give you your age, and this is the slope-intercept, which will give you the initial amount of daughter. So you have y, something we can measure today, x, something we can measure today, and then we can use that to graph and give us m, the age. So for not every dating method can utilize isochron. You have to have a non-radiogenic isotope to do it, but uranium lead can do it, and rubidium strontium can do it, and others. So these methods at least completely remove any necessity to know anything about the initial isotopic composition in terms of the ratio of parent to daughter.
Right.
I also wanted to add really quickly, for those that may not remember, and I'm really hoping that everybody in the chat does, with the equation y equals mx, the equation y equals mx plus b, y and x are obviously the x and y coordinates of the point. M would be the slope of the line, and b, I believe, is the y-intercept, where the line intercepts the y-axis.
Yeah, that's correct.
Yeah. And I also wanted to add one more thing, and that is uranium dating. And zircons are a very good material to use uranium, because zircon rejects lead during its formation. So we would expect that the original amount of zircon would be either 0 or very, very little. So we would have a reasonable assumption that the vast majority, if not 100%, of the lead in zircon is a direct result of the uranium lead decay chain.
Yes, but so you are correct that zircons preferentially reject lead because of their crystal matrix. However, they won't always 100% all reject all the lead. So, oh my God, what do we do? Well, like we talked about before, with uranium, you've got two kinds of uranium that decay into two different kinds of lead, but there is a third kind of lead that uranium doesn't decay into at all. And so if you see that, if you get any of that non-radiogenic lead, you know some of the lead was there to begin with. You can even kind of infer how much, because all isotopes of an element are chemically identical. Any process that gives you one type of lead will give you all of the types of lead. And the fact that we've got this radio... Echo! Sorry, my AI is yelling at me. Anyway, the fact that you've got this non-radiogenic isotope of lead is what lets us do, you can incorporate into the isochron formula that we just talked about. Uranium lead is particularly nice because you have two different kinds of, you have two clocks. You have the uranium-35 clock and the uranium-238 clock. And if those two clocks agree, there's no reason that should have happened randomly. And so because the two isotopes of uranium decay at different rates, one decays faster than the other, but any chemical process that removes uranium will remove them at the same rate. If there's something that interfered with the process, if the zircon wasn't completely close, and it isn't always, you'll be able to tell because your uranium-235 and your 238 dates won't agree. Now, very smart geologists have figured out how to get a date from even that kind of data, but that's Discordia, which you can look at if you want. But we can, if creationists want, we can just set those samples aside and only look at the ones where no assumptions were violated. There are so many double checks to the assumptions, which I think is a critical piece for people to remember. It's not just that a method has assumptions, because every method has assumptions. No matter what you're doing, there's always going to be some assumptions. So it's never a question of, does your method have assumptions? Well, then it's nonsense. The question is, are those assumptions reasonable? And can we tell if those assumptions were violated? If the answer to those two questions is yes, then you're fine.
Yeah. Right. Exactly. So,
there was one final point that I wanted to make in terms of radioactive decay, nuclear decay, and all that stuff. And that is that in regards to the accelerated nuclear decay, if that were a real thing, and I've said this many times, especially to people like Nephilim Free and Standing for Truth, the whole of modern physics would have to be wrong, because radioactive decay is mediated by a fundamental interaction called weak interactions, or the weak nuclear force. And the mathematics that describes that is very, very intimately connected to that of electromagnetism. In fact, they are coupled. At high enough energies, we've reached these energies in, say, the Large Hadron Collider. We know that we can take weak interactions in electromagnetism and mathematically combine them into a unified force between the two. So the fine structure constant would have to be wrong. The speed of light would have to be wrong. The Dirac coupling constant would have to be wrong.
Yep.
Electroweak theory would have to be wrong, and that's one of the most accurate, not just at the entirety of the Standard Model of elementary particles, but principally for this discussion, electroweak theory is one of the most well confirmed models, single physical models that humans have ever developed.
Yeah, real quick, before we go too deep in that rabbit hole, Creative Block asked a very important question. Snelling's objections that flowing water can produce false isochron. Are you familiar with that, Jordan?
I'm not familiar with that, but I'd be skeptical of how that would work. Flowing water, I imagine maybe he's talking about water transporting isotopes into the sample. I'm just guessing because I haven't actually seen this objection before. But that wouldn't work for like uranium lead dating because, like I said, the rate at which those two decay is different, but the rate at which they'd be added or subtracted is the same, and so you'll get discordia if that's the case. I don't know if that's Snelling's objection because I've never heard of it, but I can look into it for later.
Yeah.
Are there any other nuclear-related stuff? Because I'm going to have to tap out here in a minute.
No, I don't think. I think that should be everything. Jordan, thank you so much for joining, and I really hope you feel better, man.
Thanks.
Yeah, you take it easy, Jordan. Thanks for joining us.
All right, so Jungle Jargon in the comment section said the speed of light depends on the rate of time and the measure of distance.
Then it wouldn't be constant, and we wouldn't observe it to be the same under transformations between frames. We could Lorentz boost from a non-relativistic frame into a relativistic frame, and the speed of light remains the same. It is an invariant quantity under those types of transformations, indicating that it is constant between transformations of reference frames.
Right. So back to what we were saying about the electroweak theory. I think it's important to discuss the electroweak theory, Maxwell's equations, relativity, and the Hubble constant. I think those are pretty important concepts to discuss.
Oh yeah, I agree 100%. Sorry about that. I had to clear my throat. If we do, I don't know Maxwell's equations right off the top of my head, but I think I have a worksheet saved that I could use to walk us through just a description of what the equations mean. But I mean, the only Maxwell's equations, I guess, are important, but in regards to young Earth creationism, I think that looking at the speed of light and then how this relates to concepts in special relativity would probably be more apt for showing that we know that the universe, not just the Earth as we've already discussed, but that the entire universe is significantly older than 6,000 years.
Yep. And pretty much every single everything in physics and all the physical equations would be completely wrong if the universe was 6,000 years old.
Yes, yes. Either that, or we wouldn't be here having a discussion about how old it is.
Yeah, exactly. Just because
one of those would have to be true.
Right, just because of how catastrophic the equations would turn out to be.
Mm-hmm. Exactly. Because I mean, if you went back to when the universe was 6,000 Earth years old, yeah, I mean, if you want to know what the universe would have looked like if you could put yourself in there, whatever, look at the nearest brightest light bulb to you. Just look into it. That's what it would be, something like that, but probably much brighter.
Yeah, I think there was a question in the Cyborg chat about the cosmic microwave background. I'm trying to go back and find it. Wouldn't the CMB also pose a heat problem? The CMB is the thermal energy released when all the plasma condensed into gas, which is still pretty hot, yet the radiation cooled after the universe expanded for billions of years.
Yeah. I mean, the CMB is essentially a fingerprint that allows us to directly measure how old the universe is. If if the universe were 6,000 years old, the CMB, because when we talk about the universe being 6,000 years old, to a physicist, they're going to be looking at the universe as it would have looked if it were 6,000 years old. And back then, the CMB wouldn't have even existed yet because photons would have still been coupled to plasma.
Right.
But that's not the case, and we can look at the cosmic microwave background and use that to date the age of the universe, and what we get is about 13.8 billion years. And that's also corroborated by many other things as well.
Right. Like the most distant light is 13 billion light years away, which pretty much adds an independent check. So, how exactly is the age of the universe directly dated? I know it has to do with the Hubble constants.
Yeah, so it's essentially using the Hubble constant and then like inversing it to get inverse time. But it's not just the Hubble constant. If you use that, if I remember correctly, I think you overshoot and get like 14.6 billion years, which is still, quite accurate to 13.8 billion years. But so what you have to do is you have to factor in essentially the mass energy density of the universe, baryonic matter, dark energy, electromagnetic radiation, all that stuff, because that's going to have an effect on the dynamics of space-time, which includes its expansion rate. So factoring that in with its expansion rate now, solving for inverse time, we can go back roughly 13.8 billion years, which is corroborated by the age that we get from the cosmic microwave background.
Right. Now, if the universe actually was 6,000 years, what would the Hubble constant actually be?
Um, Honestly, it's probably somewhere around, if I had to guess, because I don't actually know the answer, but if I had to guess, I would say probably somewhere around where we're at now, because we're at the point where the universe is starting to accelerate in its
Okay.
expansion. Either that, or it would have been a little bit quicker than it is today.
Right. Which we would have been able to detect.
Hmm.
Right. All right.
And the big thing that I wanted to talk about, focus on, is something I think you may have asked me about this before, David. I'm not sure. Um, it's something that many in the chat have probably heard me discuss, and that is a I don't really want to call it an argument. I guess you could say at least an attempt at a model by creationist astrophysicist Dr. Jason Lisle.
Yep.
He calls it the anisotropic synchrony convention, and he utilizes this as a way of overcoming the distant starlight problem, which is the problem. Well, it's not really a problem unless you're a creationist, particularly a young Earth creationist. But for them, it's the problem that we can look out at the universe knowing that the speed of light is constant, and if we see a star or a galaxy that's 8 billion light years away, then that has to be the light coming from it has to be 8 billion years old. So the universe would have to have existed for at least 8 billion years, if not longer. So he overcomes this by saying, well, see, now speed of light isn't actually constant. The speed of light is infinite and then moves at half the speed of light back in the other direction. But the issue with this is he's even essentially admitted this, and I don't think he realized that he was admitting the fault in his own argument by saying this. He said the speed of light is merely conventional. It's like if you wanted to measure a table. The table has some set definite length. However, you could use a variety of different ways of measuring that length. You could use inches, you could use centimeters, you could use meters, hell, you could use kilometers if you wanted to. You could make up your own and call it Glushblins or something. It doesn't matter. But no matter which one of those conventions you use for measuring the table, that table will stay the same length. So sure, he can use a convention where the speed of light travels infinitely immediately, and then at half the speed of light, um, back in the other direction, but that doesn't actually change the speed of light. Just because you can change your convention for measuring it doesn't mean you're changing it. In much the same way that you can change your convention for measuring a table, but it's not changing the length of the table. If I measure it to be 45 inches long, and then I measure it to be 160 centimeter, actually it would be closer to about 95 centimeters long. The table didn't get longer when I measured it in centimeters because I have more of the unit. That's not how it works.
Yeah.
So that's the main problem there. The second issue is, the reason he brings this up is he says, well, look, because of special relativity, what you have is that when you want to measure the speed of light, your clocks have to be synchronized. So if you tried to take two detectors, if you wanted to send a beam of light from emitter A to detector B, and do nothing more to measure how long it took it to go from the emitter to the detector, then you could measure the speed of light. But both your clocks would have to be synchronized. They'd have to read exactly the same time. Well, the thing is that regardless of how slow you move those clocks away from each other, or rather the emitter and the detector, the devices each have their own clock, so to speak, a measurement of time. If you move them away from each other or anything, regardless of how fast or slow, they're moving. So now their clocks will no longer be synchronized, and you need them to be as perfectly synchronized as you can get them, because you want your measurements to be accurate. So Jason Lyle says, what we have to do is we have to take them, separate them, then synchronize the clocks. And then what we do is we take one, we send a beam of light out, and then send it back, and we measure the round trip that the light takes. So what you'll hear creationists say is that this is the round trip speed of light, but we've never measured the one-way speed of light, which is incoherent, because I don't even know what one-way speed of light is really supposed to mean here. That doesn't
Right.
really have much meaning. But and so Jason says, because of this, we don't know how fast light moves from point A to point B. We know the amount of time it will take to go from point A to point B and back to point A, but to go from just point A to point B, we don't know that. It could travel infinitely. You wanted to say something?
Oh yeah. There's really no reason to even believe that the speed of light behaves radically different in two different directions. There's really no solid reason to believe that. Got a couple things in the comment section. Immutable Destiny. Oh, Jason Liar. I love that guy.
But I wanted to, because the big point here is that, so he says, well, because of special relativity, we have to measure the round trip speed of light, which means that conventionally the speed of light in one direction could be any speed that you want to make it. And yeah, technically that's true, and you can reproduce the same physics we have now, but that's only because it's merely conventional. Like I mentioned earlier, it doesn't actually change anything. But the other thing is, the very premise of this entire argument that he's basing all of this on, which is special relativity, that because of special relativistic effects acting on these clocks, you have to measure the round trip speed of light. You can't measure it one way. But the thing is that one of the most I believe it's two, maybe three. Am I thinking of general relativity? It's either two or three. I think it's two postulates of special relativity is that the speed of light is constant. So the very premise that he's building his argument from, special relativity, if taken true and you follow through his argument, means that his argument is wrong.
Right.
This is a self-defeating argument that he's presented as a model. And this is
Yeah.
why it doesn't work. Also, finally, we don't need to measure how fast. We don't need to take, and I'm speaking quite hyperbolically here just to paint the picture. We don't need to take like a speed gun and measure a speed of light to figure out what the speed of light is. There are numerous mathematical techniques that we can use, and I would be happy to get into those, because there is one that is my favorite.
Yeah. So, can you ask Leo why it is the case that the famous equation of energy and mass equivalence includes the value of the speed of light and also why it is squared?
All I can say is that because that's the constant that grants the equivalence. In terms of like the deeper abstract reasoning behind why, I can Google it, but I don't know that off the top of my head.
Yeah. Yep. Yeah, and raw mechanism. When something is squared in math, it's usually because it's proportional. So yeah. Couple things I wanted to see if I have in the jungle jargon said a couple things. Try to find them. So the speed of light, I think I already discussed that. Speed of light depends on the rate measured distance.
Yeah, and
Interval direction.
that's not true. And like I said, the fact that it doesn't change regardless of your frame of reference, whether it's inertial, whether it's relativistic, doesn't matter. And I can give me just a second here. Let me see if my Apple Pencil is charged up.
Yep.
There's a I can, if you'd like me to, I can do a really good demonstration of why the speed of light is given as being constant. How essentially how we know that it's constant.
Yeah, sure.
I just gotta make sure that I get this all set up here. So chat, how's it going out there, everybody? Huh?
Yep.
I have no idea. Here we go. I just got to get the reflector app set up, and then I can get going. There we go. Okay, let me get this pulled up. Alrighty. Then all I need to do is share my screen.
Okay. 1 minute.
Alrighty, let me window. There we go. All right, I am sharing. All right, I'm going to scoot this back a little bit so I have room to bring this up. So in special relativity, there are, when you're taking special relativity or usually just relativity as a class, you'll do something, you'll work with something that are called space-time diagrams. And they're a type of coordinate space. And you have two axes. And my lines aren't going to be perfect, so I'm sorry. You're just going to have to deal with it. You have X, which is space. And it obviously you have X, Y, and Z, but the introductory space-time diagrams don't deal with things like that. They just combine space into one-dimensional and call it X. And then this is T. Now, the interesting thing is that, hold on, the speed of light would be a line coming out at a 45-degree angle like that. So if this is what your frame would look like for yourself. At any time you measure your own frame, you measure it like this. This is what most people's frames right now would look like, because they're non-relativistic. They're inertial frames of reference. But if you begin to accelerate very close to the speed of light, very interesting things begin to happen. You no longer are dealing with something like this. You are now dealing with something like this. So you can see that the axes have converged on each other.
Yeah, Immutable Destiny asked you if you could zoom in a little bit.
No, I can't. Not on this.
Yeah, I can try doing this.
I'm looking at the stream on YouTube. It looks just fine. It's probably, if you're on a phone, it's gonna look small because everything does. So
Yeah.
you'll notice, as I was saying, that the axes have converged on each other. But the one thing that you will also notice is that the speed of light is, if I could make, you know what? The lines are going to be crooked, just deal with it. The speed of light is still a 45-degree angle and is still directly in between both of the axes. What this is indicating is that the speed of light is constant regardless of your frame of reference. This right here is how we know the speed of, is one of the reasons we know the speed of light is constant. This is a more of a mathematical demonstration, coordinate demonstration of the constancy of the speed of light. But yes, when you begin to move close to the speed of light, your axes will converge onto this line, which represents the speed of light.
Yep.
So that is everybody's special relativity lesson. And that is how we know that the speed of light is constant between frames. Oh, I should have done the one about how we know the speed of light is another way that we know what the speed of light is. Would you mind if I did that?
Oh, sure, go right ahead.
While I still have everything set up.
Yeah,
Since
take
I
as
won't
much
have
time
to.
as you need.
Alrighty, let me. Okay, let's open this back up. Alrighty, now I just need to share screen again. There we go. I'm sharing my screen, by the way.
Okay, sorry. There we go.
So in electromagnetism, and I think this is more electromagnetism and a little bit of special relativity, but some people may have seen, I'm sure Immutable has an equation, C equals, I believe it's the square root of 1 over epsilon naught mu naught. I'm pretty sure that's what it is. It might be C equals 1 over the square root, but I think it's C equals the square root of 1 over epsilon naught mu naught. So epsilon naught here is a constant, and this is the electric permittivity of the vacuum of space, or vacuum permittivity. What this constant essentially tells us is it's telling us the ability of the vacuum of space to permit an electric field through it. That's why it's called electric permittivity or vacuum permittivity. Mu naught is magnetic permeability of the vacuum of space. This tells us the ability of a magnetic field to permeate the vacuum of space. These are two very important constants in both special relativity and electromagnetism, especially when you combine them. Now you take that one, and then the square root is just a way to help keep things constant and clean and nice in the equations, and that's just the way. Well, square root is actually sort of undoing an exponent, well, undoing a squared exponent, I suppose. But another interesting thing is with electric and magnetic fields, if you have an electric field that is, or rather an electric charge that is in motion, that is called an electric current. That would be essentially a changing electric field. And when an electric field changes, it can create a magnetic field and vice versa. If you had, say, the poles of some magnet oscillating or consistently reversing, you would create electric currents. So electric and magnetic fields can affect each other. And when you take that and then you figure these, what you find is that, well, electric and magnetic fields can affect each other in the vacuum of space. And when they do that, they create well, what is a wave? It is a propagation. They propagate through the electromagnetic field, these waves of energy, and they do so at a particular speed. And so what the speed of light is numerically is, I believe, what is it? C is 0.299792458 times 10 to the 8th meters per second, or 299,792,458 meters per second, or 299,792 kilometers per second. And for all the Americans, that is 186,000, Jesus Christ, 282 miles per second. So that is how we know what the speed of light is and how it is constant. We don't need to actually measure its velocity. Like I said, hyperbolically speaking, we don't need to like take a speed gun and point it at a photon to figure out how fast it's going. People who understand mathematics will find physics much easier and are probably much less likely to adhere to young Earth creationism.
Right, exactly. Sure. I think I saw a couple things in the science bar chat. Jungle Dragon, what if there's hardly any gravity? A second is 100 times as fast, and the distance is 100 times as far. That rate is a lot faster compared to where we are.
Um, do you know where that comment is at? I'm going to need to read it because okay, here it is. What if there is hardly any gravity? A second is 100 times as fast, and the distance is 100 times as far. That rate is a lot fast. I don't know what that means. What? So gravity doesn't slow down the speed of light. Gravity does not change the light's speed. I don't know if it changes its momentum either. I think it does change its momentum, but it doesn't change its velocity, or rather its speed. The speed of light is not changed in a gravitational field. The frequency of the photon will change. So a photon falling into a gravitational field will continue to move at the same speed, but it will blue shift falling into the gravitational field, and then it will red shift as it climbs out, but it will still move at c, assuming it's not interacting with any medium.
Right. Um, that's like let's see here. Perhaps it relates to my previous question. Why the value of C dictates energy? Do we know why the speed of light is it so like the speed of light is so fundamental, or is it yet unexplained?
It's fundamental because it's a constant that just really fundamentally emerges out of nature and out of a part of nature, space-time, and what space-time is, and how a very, very important field in space-time, the electromagnetic field, it tells us how that's going to relate to a lot of other things. That's why you see it everywhere. It's in special and general relativity because the speed of that the rate at which electromagnetic radiation propagates is related to the structure of space-time. It's also related to the symmetries in electromagnetism. If something can couple to the electromagnetic field in, say, quantum field theory, that's going to be related to the speed of light. So the speed of light is thereby a very important constant, and even more fundamental than that is the fine structure constant, which is also, I think, in quite a few places in fundamental physics as well.
Right. And are there any other points that you think we ought to cover?
Um, Honestly, no. I think we really did hit the big three: nuclear decay, cosmology, and then the speed of light. To me, though, those three are enough. Like, it's
Yeah.
done. Young Earth creation is on. It's done.
Right. It's untenable. I think, as I like to say, young Earth creationism is a very special type of pseudoscience, given that it is refuted by literally every single fact in every single field of science.
Yeah, very, very true.
Yeah. If it weren't for the satellites and astronauts, there would literally be more support for the age of the Earth and universe than there would be for a round Earth.
That yeah, very true. Very true. There's that. Yeah, that. I'm almost tempted to say that the age of the universe is more set in stone than evolutionary theory is, but it's hard
Yeah.
because they're both so set in stone that you can't really figure out which one is like more concrete than the other.
Yeah. Nestle asked, the speed of light is fundamental to electromagnetism. I thought it was relevant to other forces like the strong force and even gravity. Gluons and G waves travel at sea light.
Yeah, that's what I said. It's fundamental to electromagnetism because it's the speed at which electromagnetic waves move through space-time. It's fundamental because it relates to space-time, how photons move in space-time, how gluons move in space-time, how gravitational waves move in space-time. It's fundamental because it's an aspect of space-time. And that is
Right,
why it is fundamental to electromagnetism, because photons move in space-time.
right. All right, so we've been going for almost an hour. I want to give people in the cyber chat a chance to ask some questions. I'm just plugging this in. I will be on Vandalia's 1998 channel at 9 p.m. Eastern. with Dr. Dan discussing vaccinations. I am going to,
Ooh.
and it's going to be really interesting. So let me plug in a link to that. That is going to be a really interesting show. So I hope you can stop by his channel. And um, Valley 1998, COVID rumors debunked. That is what we're talking about. That is at 9 p.m. again. Um, and there is the link in the sideboard chat. So you definitely want to come by his channel, and we're going to have a really good discussion on COVID-19 and vaccinations. So feel free to stop by. So with that, any final thoughts or anything you want to plug in?
Yeah, the first thing I'll say is young Earth creationism. I'm going to steal a quote from, or not a quote, a sort of phrase from William Lane Craig, who I do admire as a philosopher and a theologian, despite the fact that I disagree with him on a lot, moving even beyond religion. Anyway, I think that a lot of people seriously need to consider the intellectual price tag of young Earth creationism. It, there is a lot of demonstrable, consistently corroborated empirical data out there that directly and irrefutably shows that young Earth creationism cannot be correct. And I think that what this comes down to is, again, that intellectual price tag. What intellectually are you willing to sacrifice to protect fundamental beliefs? And that's just, to me, that's a really big point that I think needs to be talked about. I personally am not willing to make those kinds of intellectual sacrifices for the sake of a belief or an ideology. I would rather work with something I know is corroborated, substantiated, and verified. And the other thing I wanted to say is I'm hoping this coming Wednesday that I can do a live review of Scott Clifton's and William Lane Craig's debate on the Kalam cosmological argument that was had on Cameron Bertuzzi's channel, Capturing Christianity.
Yeah. And I think it'll be really fun. I'm not sure if you're going to be down to do this, but I really want to do a review of the debate that William Lane Craig had with Dr. Sean Carroll on God and cosmology. I think that'll be really fun.
Yeah, I am down. I'd do it with you because you generally seem pretty open with doing long streams, and that one is going to be a long
Oh
I
yeah.
mean that's going to be like a 5 hour stream. That
Oh yeah, it will be. And let me know a good time and date for you to do that.
right on.
And we can do that. I think it'll be really fun to go through the
Hmm.
arguments. I will say that spoiler alert. I think Dr. William Lane Craig got destroyed.
Yeah,
But
I don't think that. I think Sean Carroll really brought very solid objections. By the way, to speed, the program on Vandalia's channel starts at 8 o'clock p.m. our time. I don't know how long they're planning to run at, but if you did still want to do Snata, you could set it for like 9:30, maybe 10 o'clock or something like
uh,
that, if that wouldn't be too late for you.
yeah, it'll probably be going probably about an hour or so. I wouldn't imagine being any more than 2 hours.
Yeah,
Um, and Dr. Dan usually is one of the people that likes to keep it to like 45 minutes to an hour.
yeah.
In my experience, he doesn't really like to do long streams. But
Hmm.
if you want to set up a time for us to do the Dr. William Lane Craig review, that'll be a lot of fun.
Oh yeah, for sure.
All right. With that, everyone, I have a couple of videos in the works for my channel, and that'll be up in the next couple of days. So you definitely don't want to miss that. Um, and I'm also trying to get my hand into some animation stuff, um, and I'll have some animation stuff coming up in the next couple months. So definitely hit that subscribe button and the bell notification down below, and hit that like button. And if for some reason you are not subscribed to my channel, you better do that now. And if you're not subscribed to Leophilius' channel, you better do that now as well. Um,
Subscribe at your own risk. That's all I can say.
one more thing. It looks like we just had one more question. Um, if I may ask one last question, I've heard Carol say that the universe has zero energy. Is that still right?
I don't know if we know whether or not the universe truly has zero total energy. It's either zero or very, 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 very close to zero, but probably zero, yes.
Yep. All right.
And all that's saying is that it's not saying, oh, the universe came from nothing. The universe is nothing. It's just saying that both sides of the equation turn out to just equal each other. That when you take up all the positive energy in the universe, and then you take up all the negative energy, it's like saying if you take +3 and then you take -3, you get 0. If you take all the positive energy and you measure it against the negative energy, they cancel each other out perfectly. That doesn't mean there isn't energy. That doesn't mean there isn't a universe. That doesn't mean the universe came from nothing. It's just saying that all of the positive and negative energy seemingly, we're quite sure that it cancels out perfectly, which is what we would expect for a truly perfectly isolated system like we're sure our universe is.
Right, exactly. With that, I think we covered quite a lot in just an hour.
Yeah.
So,
Oh, yeah. It never takes long to refute young Earth creationism, especially with physics.
Yep. All right. Good night, everyone. I will see you at 9 o'clock on Vandalia's 1998's channel.
9 o'clock Eastern, 8
Yep,
o'clock
9 o'clock
Central.
Eastern. Yep. Bye, everyone. You know what? Here we go.